mathematical technique can be used in electrical engineering and particularly in our field problems. Now, before I go into conformal mapping, there is something, that some terminology, some definitions that also you should know. Although I don't say that you have to go deep into mathematics, that's not your job or your responsibility, but you should know something. First of all, if somebody just tells somewhere, because I know many of our students will be going for higher studies later on, and then in those classes, the faculty they will use all sorts of terminology, and then you will be thinking that, oh my God, I have never heard of it. So, if somebody says that if a function is harmonic, now immediately comes to our mind, what is that? Is it like that harmonic analysis, Fourier analysis, etc.? The answer is no. The definition of a function is harmonic is very simple. It is given here in this note that if this function satisfies the Laplace's equation, then we call this is a harmonic function. And mathematically, it can be established that then the transformation of such a function via this conformal mapping is also harmonic. That means this is very important. That means, let's say I have a function which is satisfying the Laplace's equation, and then I am transforming this or mapping this through this conformal mapping, and naturally I will get another function, not the same function, but it can be proved that after the map, after is coming in, that will also remain harmonic, which means that that will also satisfy Laplace's equation. Now you can clearly understand that this is important for us. Why? Because we know that electric potential is a function which satisfies Laplace's equation, and we solve this equation to get a solution for electric potential. And that is what we are doing in this entire course. And I will get another function in that mapped version. Then mathematically it is established that function in the map version will also be harmonic, which means it will us because of it. I have to say that this conformal mapping cannot be used everywhere. It can be used only in two-dimensional fields. Well, now, Ranjan Das, can you hear? Rishabh Ranjan
Yes, sir.
Das and Pooja Datta.
Yes, sir.
Why are you joining at 11:10? What is the good reason?
স্যার স্যার আমাদের সেমিনারের ক্লাস ছিল মানে স্যারকে ওই টপিকস বলতে হচ্ছিল ওই জন্য স্যার দেরি হয়ে গেল।
Okay, who was the teacher? I will find it out.
স্যার
Aim,
Who
এম
sir.
was the
স্যার
teacher of seminar?
এম স্যার
Sir, actually,
Aim.
Yes, sir.
Yes, what?
sir, actually, there was
Yes,
a problem with the scheduling of the class. So, like,
what
it
there was?
accidentally overlapped.
Uh-huh.
And sir, AM
Oh,
sir said that it will take just 10 minutes for us to inform him the topics.
oh my God. Okay. Anyway, let us again go forward. So now this conformal mapping can be applied only for two-dimensional field. Now you all know that this two-dimensional field I have already earlier explained. It means that the potential field is translationally invariant along any one of the three. Example is electric cables, where the field does not vary along the length of the cable. This I have already explained to you in one of our earlier classes. Now, because of this property of conformal mapping, that the functions remain harmonic in the the real life function as well as the mapped function, so they can be applied in many different areas, and some of these are here mentioned. As you can see, it can be applied to static electric field, it can be applied to static magnetic field, static electric field, stationary thermal field. And in these cases, you will see they use basically function which satisfies Laplace's equation. And the mathematically speaking, the fundamentals of this conformal mapping, etc., that is based on something which you might have gone through long time back in your first year or so classes, which is called the Cauchy-Riemann theorem. Now, this is basically again according to the Riemann mapping theorem, but I am not going into those things. That is not part of our syllabus. We will like to see how we can apply this. So, before that, I give you some very basic theory of conformal mapping. What we are doing. Now, let us say that we have a function z is equal to x plus iy. Now, it's a complex function, but it's a very common function. And we are saying that there is a complex variable, some which is shown here. That means z is a complex variable. Then fz is a complex variable function, which also has two parts, real and imaginary parts, u and v. Whereas the z, which is the complex variable, has two parts, x and y, the real and imaginary parts. But this x and y are real numbers. They are not complex numbers, whereas z is a complex quantity. Whereas fz is a complex function which has two real and imaginary parts, and both these real and imaginary parts are actually functions of z, and therefore it's a complex one. So u is a function of x and y, v is also a function of x and y, and this x and y is coming from z. So this is our starting point of conformal mapping, that we should have a function fz like this. Now, a little bit of derivation, that we are saying that uh, it will satisfy Laplace's equation. Now, if you remember the Cauchy-Riemann equations, if you don't remember, doesn't matter. I have written it in 11.1 that these two are the very well-known Cauchy-Riemann equations, which actually correlates the first order derivative of u and v in terms of x and y. So these are the two equations. Now you see we are doing a little bit of mathematics here, so which is shown here. So if I say del to u del x square, then I can definitely write it as del x of del u del x. Then from Cauchy-Riemann equation, this del u del x can be replaced by del v del y. So it becomes del 2 v del x del y. Then we are rewriting it as del y of del v del x. Then del v del x can be again rewritten from Cauchy-Riemann equation as del u del y. So it becomes minus del 2u del y, del square y. So you take it on the left hand side, you get 11.2. But when we look at 11.2, interestingly, this is the Laplace's equation in two dimensions, which clearly shows that this function u, which is actually nothing but the real part of the complex function, variable function fz that is harmonic. That means this function, which is in the mapped domain, that also is harmonic because it satisfies the Laplace's equation. And just the way we have derived 11.2, you just do it on your own, and you can also prove very easily that 11.3, that is del 2 v del x square plus del 2 v del y square will be 0. So that means it also satisfies the Laplace's equation, and therefore we say it's another harmonic function, which means that these two components of fz, that u and v, they are both harmonic functions satisfying Laplace's equation, and that is primarily the basic foundation of the conformal transformation. Now, how we are mapping? This is our second point, the mapping of shapes. Now, if I ask you that if I write z is equal to x plus iy, what do you really get? Say I am giving you x coordinate and y coordinate. This is nothing but x coordinate and y coordinate. Z is equal to x plus iy. Then, if you plot it with x and y axis, this z is equal to x plus iy is nothing but one particular point, which is shown at the bottom. That means if I define this xy plane as the z plane, then this point will have a particular value. This value will be complex because it has a real and imaginary part, and that complex value will be this black dot. And now I am saying that I have defined, as per our earlier discussion, this fz, and then I have applied that on this back point, that is z0. Then it will go into the w plane because fz, if you again look into it, fz has a real part u and an imaginary part v. So I plot this instead of x and y, I plot x-axis is u, y-axis is v. And then this point z0 is mapped to the point w0 on the uv plane, and I am saying this is the w plane. Now this is basically the mapping between z plane and w plane, and how it is being mapped by introducing a function fz. Now don't bother about fz, I will tell you about fz later. But just for the time being, assume that there is a complex variable function fz in that mapping. Now there is some interesting point here, that look at that z plane, and if I ask that what will be dz, an incremental change in z, naturally answer is it will be dx plus idy, which you all can understand. And similarly, if I say what will be dw in the w plane, then it will be du plus idv. So these are well accepted. So therefore, from these two expressions, I can find that modulus of dz square is nothing but dx square plus dy square. Similarly, modulus of dw square is du square plus dv square. And dx, du, dv, these are all incremental changes in the xy plane or on the uv plane. So therefore, on the z plane, square of the length element, right? Any small length element dl, that must be the dl square, that must be equal to modulus of dz square. That you can all understand. So this is nothing but dx square plus dy square. And on the w plane, similarly, if I take a small length element, the square of the length element, here I am saying capital L to represent it on the w plane, and the small l is represented on the z plane. So dl square is du square plus dv square, which is modulus of dw square. Therefore, if I know this, then I can say that dl that is d capital L dl. That means the derivative of the length element on the W plane with respect to the derivative of the length element on the Z plane, that becomes dw dz. Now remember, W is the complex variable function. We are also saying this is as mz. So this is nothing but the first order derivative of the complex variable function which we have taken as the mapping function. So we say that uh, this is an important statement in conformal mapping, that if there is a finite slope at any point, then the ratio of the length elements, see, ratio of the length elements is dl by dl. That means d capital L is a small length in the W plane, d small l is a small length element on the Z plane. So d capital L by d small l is the ratio of the length elements. And if the slope of, there is a finite slope, then this ratio of the length elements close to a particular point remains constant. That means the net result is to change the dimensions in equal proportions and rotate in infinitesimal area in the neighborhood of that point. Now, this rotation I will explain. What is rotation? That in general, yeah, now you can see highlighted part. I am assuming an fz. Fz is a complex variable function, so that I am taking as z plus b, where z is a complex variable. And a and b are also complex numbers. So it's a fully complex variable function. Now, if you multiply something by this, basically now try to understand what is happening to, that means z is a variable on the z plane, and you are multiplying this by fz, and then you are getting it on the w plane. Then what is happening? It is happening that when you multiply z by a, and a is a complex number, then what you are doing is you are multiplying the magnitude by the modulus of a. But this a being a complex variable, then it has an argument. So when you are multiplying z by a, what you are doing, you are rotating it by the angle which is given by argument of a in the anticlockwise direction. I repeat, z is on the z plane. I am multiplying it by a complex variable a. Now a has an argument as well as a has a modulus. So the magnitude of z, that will be multiplied by modulus of a, and we always say that this will either dilate or compresses a, compresses the z. And then we are multiplying it by a, and a has an argument which is nothing but an angle. So basically you are rotating this z by the angle which is represented by argument of b is also a complex number. Then after the multiplication and the rotation, whatever you are getting, then translate it by b. Plus b means nothing but the translation. Therefore, one very important thing is that thus the ratio of linear dimensions, which may also be represented as the angle, is preserved in conformal mapping. That's a very important aspect. I am going to explain it after some time. Now, another terminology or definition I would like to mention here, which you may not have heard it. You have heard many things, equipotential, isothermal, this, that, etc. But there is a something called isogonic. Now, I don't know whether you have heard it. Isogonic means that where the angles are preserved. Like isothermal is something where all the temperatures are same. an isopotential or equipotential where all the potentials are same. Then isogonic means that the angles are preserved. Please remember this definition. And this is why it is important, because in conformal mapping, therefore, what happens that if I have two curves on the z plane which are intersecting at each other at a particular angle, and by applying fz when we are mapping them onto the w plane, we get two more curves, but they are different on the w plane, but they will intersect at the same angle. This is the isogonic property of conformal mapping, and this is so important for us because here you can see on the highlighted part. This is important for electric field analysis because equipotentials and the field lines, we all know that in electric field theory they are normal to each other on the z plane. Now, if I map it by this fz onto the w plane, and if this orthogonal property is not maintained, then we'll not get the solution, or rather the correct solution. But conformal mapping being isogonic, these angles are being preserved, and therefore the curves which are normal to each other on the z plane, which means equipotentials and the electric field line, will remain mutually orthogonal on the w plane, although the shape may be different. And just a little bit of again mathematics, that if I do something like this, that if I take f dash z into f dash w, that is the first order derivative, one in the z plane, one in the w plane, then z plane it will be dw dz, then on the w plane it will be reverse, so it becomes 1, which means that the inverse mapping is also conformal. That means whatever what a system I got on the z plane, I can map it to the w plane by applying an fz function, and then instead of getting the solution on the z plane, which is our real life plane, I get the solution on the w plane, and then I do the inverse mapping and get the solution on the z plane. That's the entire concept what we are going to apply. Interestingly, we say that if our shape, because so far we were only considering about the one curve or one line, but in our electrical field theory, we'll have shapes like electrodes and boundaries. So this shape, if it is very small, infinitesimally small, and then if that small region in the z plane is transformed to the w plane, this remains same. That means the rectangle will remain same. However, if this is in a large scale, that means if the dimensions are quite large, then the shape will not remain same. This shape remains same only if it is infinitesimally small region. Now, why it does not remain same? Because dw dz, depending on the shape, if it is large, it will vary from point to point on the z plane. And if the slope changes, then we have proved that the ratio of the two length elements keeps on changing depending on the slope at a particular point. So if dw dz change, the ratio of the length element will change, and therefore on the mapped plane you will get a different shape. But please remember that the isogonic property will be preserved. That means the angles will be preserved. Now, this can be proved mathematically. Whatever I am telling this isogonic property, and some of you who like mathematics, you will like it, and those who doesn't like mathematics, for you it might be a problematic. Anyway, what I am trying to show you is these two diagrams. First one on the left is on the z plane. So you can see x and y on the z plane, and I have A and B, two curves, and they are intersecting at the point zi, because remember any point on the z plane is represented by the complex number z. So I am saying this point is represented by zi instead of saying x and y. I am saying zi. That is the way we represent in conformal transformation. And then what is the angle between the two curves at the intersecting point? This you all know from your plus two level knowledge, where you have done very good mathematics. After joining Jadavpur, you have all stopped mathematics. I know that. Don't tell me anything. I know from my last 35 years experience in Jadavpur engineering, nobody does mathematics. This is a very, very sad affair in Jadavpur. So I can take two tangents on the curve, that is tangent of curve A at the point zi, tangent of curve B at the point zi, and then the angle between the two tangents is the angle between the two curves at the intersecting point. So should be U and B. So So this A prime and B prime are the two curves which are the mapped versions of the curve A and B on the Z plane, and they are also intersecting at one particular point. Then I am taking two tangents. One is the tangent of curve A at W, tangent of curve B at W, and the angle between them is beta. Now I am trying to say that the mapping is isogonic. That means angles are preserved. So this alpha must be equal to beta. Can I prove it? So it is done in this way, that if you remember your knowledge earlier, equation 11.9, that can be cos of alpha can be represented in this form. And similarly, cos of beta on the W plane, cos of alpha is on the Z plane, cos of beta is on the W plane, it's the equation 11.10. Then what we are trying to say is that let a curve is parameterized on the z plane by z is equal to zp, and the complex analytical function is fzp. This we have already discussed, because this function is actually the mapping function. Now there is something in called in mathematics which is called chain rule. So if we apply chain rule, then W is equal to FZP will give me that T dash W, that will be equal to F dash ZP into TZP. That means tangent at the W is tangent at the Z plane multiplied by the first order derivative of the uh, that mapping function FZ. So therefore we are saying that the curves are intersecting at z is equal to zi. So therefore, I am writing that for the curve A, TWA from the chain rule application, I am getting this, which is coming from the previous line. Similarly, TWB as the application of the chain rule, I am getting this. And of course, the first order derivative must be non-zero, otherwise this entire analysis will not be valid. So we are saying f dash at zi, that means the first order derivative of fz at the intersecting point is non-zero. So we can write equation point 10, that means cos beta here. Here you can see TWB, TWB, etc. And we have written here two functions for TWA and TWB. So we replace it. We get 11.11. And then we eliminate the absolute value of f dash z, which is non-zero, so we can cancel from numerator and denominator, and therefore I get cos beta 11.12. And if I look at 11.12 and if I look at 11.9, I will find that alpha is equal to beta, which proves the isogonic property of conformal transformation. Now, so far I have given you all the theoretical and this thing. I am pretty sure you have not understood it. In fact, when I was first going through it, I didn't understand. So, I give you a problem to explain the whole thing. Just read it. What is the problem? I am saying that there is a point on the z plane given by 1 plus I. That means x is equal to 1, y is equal to 1. Find the mapped point on the w plane. Under the linear transformation, W is equal to this. That means this is my Fz. That 1 plus Iz plus 2 plus 2I. Now remember, look at this. This is nothing but that previous form I have said. Az plus B. Right? This one. Earlier I told you that Fz will be represented in the form Az plus B. So here you see A is 1 plus I, B is 2 plus 2I. So what we are saying now as the solution that Fz is represented on here you see Az plus B, where A is having a modulus which is root 2. It has an argument e to the power I pi by 4. That means the argument of A is pi by 4 and B is 2 plus 2I. So remember that our steps, what we are doing, we are taking Z, then we are multiplying it by the modulus of A, then we are multiplying it by the argument of A. So look at here. I have on the z plane x and y is the point P which is 1 plus I. Then I'm multiplying it by root 2. Now intentionally I have not given any x and y axis because this is just step by step to show you. First I'm multiplying it by the modulus of A which is root 2. So what happens, the length OP is changed to length AB. Keeping this angle pi by 4, that means 1 plus I has an angle pi by 4 with y, so that angle remains same, only the magnitude is changed because I have multiplied only by the modulus of A. Then you remember that I said that I have to rotate it by this argument of A. So how I am doing? So this is the second step, step 2, that now the changed length AB is rotated by an angle pi by 4. Why pi by 4? Because it is the argument of A in the anticlockwise direction. So visually, now AB is this length now. Now this will be rotated on the diagram C by pi by 4 in anticlockwise direction, and we will get the length AC. So you see the point P was first shifted to point B by the multiplication of the modulus of A, then this is rotated to point C by an angle which is argument of A. And now the third step, that is this B, that is 2 plus 2y. That means now I am saying step 3, that is it is translated by 2 plus 2I. That's the last step. So now on the diagram D on the right side, you see the point C is translated by 2 plus 2I, and we arrive at the point P prime. Now this is my W plane, W plane. Again, there is a mistake on the y x-axis, not W, it should be U. So look at diagram A, which is XY, and my point was P, and therefore the length element was OP. But now this has been mapped to the point P prime on the W plane, and now my length element is O prime P prime. This is exactly the conformal mapping. This is the mapping of one particular point as given in this problem. That means the point z is equal to 1I is mapped to the W plane by this function W is equal to this. Now to make it even more elaborate, I have given a second problem. What is this? I am saying that I have a rectangular region. I am saying omega, capital omega in the z plane. And this rectangle is naturally bounded by 4 straight lines. And I am saying, what are these 4 straight lines? These are the 4 straight lines, which are the bounding straight lines of the z plane. So now the problem is this, that I'm having this fz function, which is same as the previous problem, but find the mapped region. Now it is no longer a point, but the mapped region on the W plane, which is capital omega prime. This is exactly what we are going to do in conformal transformation, where an entire shape will be, mapped to the W plane. So now we are saying this is my W. Now we are, you remember I defined earlier that W is equal to U plus IV. So we have taken the real part on the right and the imaginary part. So you see real part is x minus y plus 2, imaginary part is x plus y plus 2. So u is x minus y plus 2, v is x plus y plus 2. So what we are saying now, that for x is equal to 1, if you put here, you will get this expression. That if for x is equal to 1, you will get an expression for u and v. And from there I find this equation is u plus v is equal to 6. Now u plus v is equal to 6 is definitely a straight line on the w plane. So that means x is equal to 1, which is a straight line on the z plane, is mapped to a different straight line on the w plane, which is u plus v is equal to 6. Similarly, if I take that y is equal to 1, then you can find out that this y is equal to 1 is a straight line which will be mapped to another straight line, u minus v is equal to minus 2. Then the third straight line, x minus 3, x is equal to 3, it will be mapped to a straight line u plus v is equal to 10. And the fourth straight line, y is equal to 2, will be mapped to a straight line u minus v is equal to minus 4. So these four straight lines, x is equal to 1, y is equal to 1, x is equal to 3, y is equal to 2, this is defining a rectangle. They are mapped to four different straight lines, and then if I plot them on the w plane, you can see that I am having this region capital omega prime, where these are the four bounding straight lines, which the equations I have already obtained earlier. So x is equal to 1, here is AD is mapped to A prime D prime, where the equation is u plus v is equal to 6. Similarly, AB, which is y is equal to 1, is mapped to A prime D prime, which is u minus v is equal to minus 2. So in this way, the rectangle here shown is mapped to a rectangle on the W plane, but first of all, their magnitude, the area has been changed because there is a multiplication by the modulus of the fz, then there is a rotation involved here, which is also the argument of the fz, that az plus b, and then finally there is a translation. This is how a shape is being mapped from z plane to w plane. So from here we bring in a function concept called complex potential. That means this is, again, I am saying very well known that fz has two real and imaginary parts. And instead of writing u and v, now I am writing slightly differently, phi and psi. And here I am saying that that real part phi is representing our electric potential function, and uh, this psi, which will be the another function on the w plane, that will also satisfy Laplace's equation, maintaining that isogonic property, that is the angles. So therefore, this complex analytical function is known as complex potential, and Laplace's equation is being satisfied. What we are saying is that this fz real part, this fxy, we are saying as our real potential, that means the real life electric potential. Then phi xy is equal to constant. If I take this curve, this will naturally represent an equipotential on the z plane. Since I am saying that these are two orthogonal, because u and v, they are definitely orthogonal. So phi and psi are orthogonal. And if phi is equal to constant represent equipotential lines, then psi must represent electric field lines, because we know electric potential, equipotential and field lines are orthogonal. So therefore, psi that represents electric field lines on the. So therefore, uh, what is the, I mean, how does it help? That I have written here, so you can read it later on. That the introduction of this concept of complex potential, what we get from here is that we can handle equipotential and electric field lines simultaneously as the real and imaginary part of the complex variable. Then by mapping of these shapes, a difficult geometry on the Z plane, that means the real life plane, can be mapped to a relatively simpler form on the W plane, and then the solution can be obtained on the W plane and mapped back to the Z plane. And this is precisely explained as the procedural steps in solving problems using conformal mapping. So what we have to do, find an analytic function. First, I have to find an analytic function fz, by which I will map the original region in this on the z plane to the transformed region on the w plane. And then this region, which is on the w plane, we are going to have the solution on that. But for that, the boundary conditions has to be transferred from the z plane to the w plane. That means equipotential, we have to say what is the potential on the z plane, that has to be transferred to the w plane, and so on. So boundary conditions has to be transferred, and then we solve the problem, because this complex potential function satisfies Laplace's equation. So we solve the problem on the w plane, where our assumption is that the geometry will be relatively simpler on the w plane, and that is the primary target of conformal transformation. And then finally, we get the solution f dash w on the w plane, but we now do the inverse mapping and come back to the z plane and get the solution on the z plane, where z plane is our real life plane. So it looks like this, that first I have a shape here, the region that I was considering on the z plane, and then this has been mapped onto the W plane. On the right side, of course, the shape is now different, but now this complex shape on the Z plane is having a well-known shape on the Z plane. Let's say it's an elliptic shape. And then boundary condition, say if it is an equipotential, then I will say same boundary condition will be applied here. And then I'll find the solution on the W plane. And this is the solid potential on the W plane, and the real part will represent the electric potential, the imaginary part will represent the electric field lines. And the same thing now mapped back to the real life, and I get the solution for the real life problem. So this is how we solve. So now I am giving you a very specific example, that conformal mapping of coaxial cylinders. So diagram is something like this. On the left you have the coaxial cylinder. It is a two-dimensional field. You know that it is field is translationally invariant. So the inner circle or inner cylinder is an equipotential, and if the radius is r1, then equation is x square plus y square is equal to r1 square. Then if I have the outer sheath or the outer cylinder, it is also an equipotential, and if I am saying this is arc potential and the radius is r2, the equation is x square plus y square is equal to r2 square. Then any radial line will be normal to these two circles or the cylindrical surface, and these radial lines will then be the electric field lines, and each radial line will have a certain angle. So therefore, they will be transformed to this W plane following the conformal mapping, which means that the equipotential and these field lines, they should have 90-degree maintained on the mapped plane. I will show you now here that we start always with a function fz. Now here is my function fz, that is here. That is C1 ln z plus c2. This is the function that we are assuming. Now you can ask me, how did you get it? Well, this comes from the mathematicians who know which function has to be applied where. And we engineers take those cases and apply. Now here if I write z is equal to x plus iy, and you know x plus iy can always be represented as r e to the power I theta, so that r is square root of x square plus y square and theta is tan inverse of y by x. And then u plus I v, and if I put z is equal to r into to the power I theta, then you can see that u can be written as c1 ln r plus c2 and v can be written as c1 theta. So now I have got u and v and they are functions of r and theta. Now for the inner conductor, x square plus y square is equal to r1 square. Now that is naturally it is equipotential, but now look at it that what is it here? See, what is my u1? U1 is here. So if I put r, a particular value, that is r is equal to constant, then u also becomes constant because c1 ln r plus c2 that becomes constant. So I get u1 for this x square plus y square plus r1 square. u1 is equal to constant, but I get a straight line. Therefore, what is this u1 is equal to constant? On this right hand side, you can see this is a vertical line parallel to the axis. Similarly, if I put r is equal to r2 corresponding to the outer cylinder, I get another vertical straight line which is on the right side. So I have, instead of two cylindrical electrodes, now I have two straight lines which are representing my two potentials, that is the electrodes, and therefore this has been transformed into a parallel plate electrode system. So you can see I was telling that this transformation will make it much simpler. So this cylindrical electrode system has been transformed to a parallel plate electrode system. And similarly, anything which is normal to the equipotential line, that means V is C1 into theta. So if theta is equal to constant, I get V is equal to constant. So therefore, uh, let's say this first line theta is equal to theta 1, then this will be transformed to a straight line C1 into theta 1, which will be parallel to U axis. So here you see this parallel. Similarly, this radial line theta is equal to theta 2 will be transformed to V2, which is C1 into theta 2, again another horizontal line. So you can see now that the vertical lines are equipotentials and horizontal lines are the field lines, and this, therefore the isogonic property is perfectly maintained. That means they are orthogonal to each other. So this shape on the right hand side, by means of this transformation shown at the lower side, that C1 ln z plus C2 has been transformed to this particular parallel plate system with the electric field lines normal to the electrodes. Then how do I apply the boundary conditions? Very simple, that for the this this first electrode, which is the live electrode corresponding to the inner cylinder, equation is C1 ln R1 plus C2 is equal to V. So then we write that C1 ln R1 is equal to V. And then for the outer cylinder, this is the other vertical line, C1 ln R2 plus C2, that is equal to 0. That is equation 11.17. So now I have two equations, 11.16 and 11.17. I straight away solve C1 and C2, the two coefficients, and then I put back into the equation. This is the equation for U, which is electric potential. I immediately get the solution. So I get the solution of phi, which is 11.19. If you want any component, then of course you can take the derivative, you get the field intensity component. So this is what we do in conformal transformation. But then you can say always that cylindrical system of course can be solved analytically. Why are you showing us this? The answer is yes. it is a simple system I am showing you, but this is because it helps in the understanding of conformal transformation. But conformal transformation is definitely not developed for such simple system. There are many other geometries which can be mapped to a simpler geometry, but that is not required for your course. For your course, it is important that you know there is a method called conformal transformation. What is the basic methodology in conformal transformation and how do we apply? This is what I wanted to show you, and that actually, yeah, this is the end of the note, and therefore I stop here. So this note I will send you. Uh, so if you all agree, we can close the class now. So you can log off.